and how they work. In this nugget, we're going to take a look at some of the most common application layer services that we're going to run into on a daily basis as we work on the networks. And we're going to learn what the actual well-known ports or numbers are assigned with those application services. It's a lot of fun, and the information we're going to learn in this nugget is going to serve you over and over again as we work on computer networks. Let's jump in. So our objectives in this nugget are to identify common TCP and UDP ports. I mean, the whole goal of it is right here. And we could just look at these common ports, memorize them, and be done. But you know what? I wanted to reinforce the concepts that we previously learned about how the networks operate, and then you can fully appreciate these ports and exactly what they do. So let's go back to the big picture, and let's say that this PC right here wants to talk out to the internet. How does it do that? What needs to happen? Well, we have to have some connectivity. So logically, the path of the traffic will go out here to the internet. If we're going to, for example, Google.com, which a lot of people go to quite often these days. And so we're going to use different services to get there. So let's imagine this PC is going to make a request. Now, the type of request is going to drive the type of port number we use. So for example, Google.com over here is actually listening on TCP port number 80. And that's called a well-known port. Now, why is that a well-known port and why is that a good thing? Well, if we didn't have some standards in place, for example, yeah, Joe, you go create a web server and you just kind of listen on whatever port you want to and hopefully you'll have a customer, that wouldn't work out too well. So here's a standard. Anytime you want to have a web server, the default port at the application layer that you're listening on is going to be port 80. And so the client over here knows, well, if I'm going to make an HTTP request, so I have a browser that's about to go to a website, at the application layer, we're going to request the services of TCP down here, and we're going to go ahead and request the destination port. You can kind of think of it like an application identifier for HTTP, port 80. So if we send out traffic, it'll be sent to the well-known port of port 80. At layer 3, at layer 4, we're going to use TCP because that's what HTTP wants to use. At layer 3, we're going to use IP, so it'll be destined to the IP address of the Google server. At layer 2, we're going to use whatever frame type's appropriate for our network right here. And because this is an Ethernet network, we're going to use the Ethernet standards, and then the bits are going to be pumped out one by one, and they're going to go through the switch to the router, and then the router is going to look at it and make a forwarding decision based on the IP address. So that's the play-by-play. So the whole goal here is to have some well-known ports so we know who to go ahead and reach. So I say we try some of these. So I've got a PC right here. We'll bring him into the picture. And from our previous discussions, this PC is the PC that's sitting right here on our network. So we wanted to just verify that. Do you remember how we could verify the IP address of a computer that we're sitting at? Now, from our earlier discussions together, we said on a Windows machine it was ipconfig. And sure enough, this is the 10.1.0.51. And this IP address that we have, we also know that the first 3 octets are the actual network because of the mask. So the 255, 255, 255.0 means the first 24 bits of our IP address are the network, and the last octet, this last number, is our actual host address. So if you haven't been through the IP addressing nugget yet, you got to go back and do that one first so you can build upon that knowledge. We also have information on a default gateway. Now, what's the default gateway? The default gateway is really simple. It's the PC's way of saying, I know how to reach the 10.10 network and anybody who lives there because that's my same street. However, if this PC needs to reach somebody outside of his local street, he will go ahead and use his default gateway. Now, what that really means, too, is that he's not going to forward a packet at layer 3 to his default gateway because if he's going out to the internet, he needs to use the IP destination address of the Google web server. However, to use this default gateway, he'll simply, when he writes the layer 2 frame, he'll put the destination layer 2 address of the router, so the router will get it, de-encapsulate it, look at layer 3, see the destination IP address, and then make a routing decision. See, the cool thing as we discuss this together is that we're building and reinforcing everything we've learned in the previous nuggets, and it's going to continue like that for the duration of our sessions together. So again, I encourage you to take these in order. So here's our PC. It has a default gateway. Let's go ahead and have him go out to google.com. So we'll close that command prompt. We'll open up a Windows browser and we'll go out to let me maximize this as well. We'll go to www.google.com. So now that we're there, let's take a look at the protocol analysis of what exactly happened in the background that made it all possible. And I want to focus here on this destination port of port 80. So although our conversation between this PC and the Google web server took quite a bit, I want to focus right now just on the one of the initial packets that went out to that device. And I also could say one of the initial segments. So here we have a protocol analysis of some traffic that went out, and I'd like to go ahead and look at this from the ground up. So at layer 1, it captured 4,368 bits, which equals 546 bytes. We look up at layer 2, it's going to have the source MAC address of my computer, and we could verify that real quick. I could just bring up my computer over here, and if we want to see the MAC address, we can do a show our ipconfig/all. They'll give us all the details. So if I scroll up a little bit here, here is our MAC address, and that is 001B77, ending with 123456. Looks like somebody hard-coded that to make it easy to identify, which is what I did. So we look at this source MAC address right here. The source MAC address is 001B77, 123456. That's the MAC address of my PC here. And I sent it, because it wasn't on my local network, I sent it to the MAC address of my router. So my router is right there, and we'll take a look in a moment at exactly how we learned that. So that's at layer 2. Also at layer 2, it knows it's handing it up to a layer 3 protocol of IP. See that number right there? Hexadecimal 0x means it's in hex, and 800 means it's the layer 3 protocol of IP. So in the layer 2 header, it had the source MAC address, the destination MAC address, and it included the actual layer 3 protocol. Most of our traffic is going to be dealing with IP at layer 3. And so at layer 3, if we take a look at this layer 3 header, it's got the source IP address of 10.10.51, that's my PC, and the destination IP address of 74.125.227.84. Now, hang on to this thought. How did my computer know that was the IP address of google.com? Because we'll take a look at DNS here in just a little bit. But the point, the piece de resistance for this packet is I want to take a look at layer 4. So at layer 4, we're using TCP. Now why? Why are we using layer 4 TCP? And the reality is that when we make an HTTP request to go to a web server, the rules, the standards, the protocol for HTTP says that it wants to use TCP at layer 4, so that's what it got. It also, when you connect to a web server, it's going to connect to the well-known port, the destination port of 80. Why is that? It's because that's the standard that's in place. So if you and I want to create a brand new web server, we can put it up, get it an IP address on the internet, make sure it's paying attention at the application layer to port 80, and then people can send a request to us, and our computer will listen, and if it's running the right software, it can reply. So right here, let's take a look at this for a moment, because this is extremely interesting. Right here, we have a destination port of 80. And that's because it's an HTTP request. So in the layer 4 header, which we're looking at right here, it's contained, let me get a different color. It has the information about the application layer data. So it started up here as an HTTP request. It requested the services of TCP. We're sending it to the well-known port of 80. I also want to point out this source port. Now, how did that happen? This computer right here is amazing. Let me tell you how amazing it is. This computer could open up a browser, a web page to Google and Cisco and Juniper all at the same time. If all those sessions were open and the reply traffic's coming back, how is the session layer, which is part of the application layer here in our TCP/IP protocol suite, how is it going to keep all those straight and keep them intact? The answer is it's going to use unique port numbers at the application layer to keep it straight. So this PC said, I'm going to make a request out to google.com. I know the destination is the well-known port of 80 at the application layer, and I'm going to pick the unused on my local computer port of 1048 to track this session. So that's really an application layer function, and the information for all of that is inside of the TCP header. Again, you know, the OSI reference model is just a model. Not everything fits exactly perfectly in. This is one of those things where the TCP header, it contains the port numbers, which is really being used by what would be the session layer of the OSI reference model, which is bundled into the application layer. So there's the destination port, the well-known port. And then at the application layer, we have our hypertext transfer protocol, which is being used for the language of love for HTTP. So what have we learned so far? Common TCP and UDP ports, so far we've identified one, and that is the well-known port of 80, which is used by HTTP. So HTTP uses the TCP port number 80 for tracking for the destination. Okay, so what other protocols do we have that we might want to be aware of? Well, how about HTTPS? What's the difference between HTTP and HTTPS? Well, you might say, well, Keith, there's an S there. Yes, there is. But why do we use it? Well, let's say we bring in back our same client and we want to go to a secure website. We don't want the possibility of an eavesdropper seeing all of our data. So let's go out to https://www.paypal.com. Now, what's happening in the background is we're not just establishing a normal HTTP session, which is people can eavesdrop on that. HTTP is not encrypted, it's not protected. With HTTPS, you see this little lockdown here. With HTTPS, it's actually building a secure pipe, a secure path, if you will, between my PC in this case and PayPal. And that's what the benefit of HTTPS is. It uses a different port. If we looked at the protocol analysis for this one, it would say that the destination port at layer 4 in the TCP header is 443. Do you get the drift? All we're using is unique port numbers which are associated as well-known ports with services so that we can track sessions and get to well-known services out there, such as a secure web server. Let's do a couple more. Let's maybe bring this out of the way so we can see our graphic. Another well-known port that's used all the time are well-known ports used for applications for email, as an example. These three applications right here, the Simple Mail Transfer Protocol, which uses the well-known port of 25, POP3, which is used to get email, which is port 110, and IMAP, which is 143, are all very, very popular and very commonly used email applications. So why do we care? I mean, Keith, why do we have to memorize these numbers? Well, let's say that you and I are in charge of this router, and our management comes to us and says, hey, we want you to filter, to put an access list to stop any traffic if it's email based. And what we could do is we could start by saying, well, email. So what we'll do is we'll put a filter in place that's blocking on TCP what? Well, any traffic trying to go to TCP port 25, that would block SMTP. And any traffic going to TCP port number 110 and also TCP port number 143. That'd be a good start. Is that the only way we could? Are there other possibilities for people squeaking email by? The answer is yes. They could use a non-standard port, but that would be a very, very good start. So other applications. Let's say that you and I are in charge of managing this branch office router right here. So that's our job. We want to manage this branch office router, and yet we are here. So we're at the headquarters office. We need to manage that. How do we get to that router to manage it? Well, we can use a remote access type of protocol, a set of rules, and there's two that are primary. We have a thing called Telnet and a thing called SSH. So let's apply this. Let's go ahead and let's say we're sitting at the PC here on the far left, and we want to run Telnet to talk to this router. Now the first question is, what is the IP address of that router? Now, I happen to know it is 192.168.0.3. That's one of its IP addresses. Now, how do I know that? It's because I configured it. So to use Telnet, we would simply go to a command prompt, and from the command prompt, now Windows 7 doesn't have an built-in Telnet program, but Windows XP does. So there's a lot of free, like PuTTY is a free application that will do Telnet and it will do SSH as well. So let me clear my screen. Let's do a Telnet to 192.168.0.3, which is the IP address of this router. And let's see if we can connect. There we go. That's a healthy sign. Now, this is the command line interface prompt of R3, and what we're using is Telnet. Now, what I didn't do is I failed to capture that. So let me go ahead and capture that traffic, and we'll do it one more time real quick. Now that I know it will work, and we're capturing, we'll do a Telnet to that IP address, and then let's take a look at the capture together. So let's take a look at what just occurred. So we bring in the protocol analyzer. At layer 5, or the application layer, we have the application layer service of Telnet. And Telnet requires or requests the transport layer of TCP, and it also goes to a well-known port of 23. So at the transport layer, if we take a look at the destination port, the destination port is 23, which means my router over here is acting as a server. It's listening on port 23 and saying, yeah, I'm willing to accept connections, and that's the reason I'm able to communicate with it. I'm using 1068 as a source port. Do you know why? We took a look at this earlier. I'm using that as a source port because I can. Now the PC said, you know what? I need to track this session. I'm not sure, I might have multiple Telnet sessions happening with, multiple devices. So it spins the big wheel, grabs a free unused port on my local PC, and uses that for this session. When this session is over, that port number is gone, and the next time I generate a session, I'll very likely have a different port number altogether. So as traffic goes out to the IP address of my router at layer 3, at layer 4, it's going to have a destination TCP port of 23, a source port of 1068. When the router replies back to me, the source address of the router will be in layer 3, the destination IP address will be my IP address of the PC, and these two port numbers will be reversed. So the source port will be port 23 for the return traffic, and the destination port will be 1068. And that's how my computer, for inbound traffic, can keep track of saying, oh, this is for that Telnet session that I generated a few moments ago, and that's how it tracks all that information. Okay, so the well-known port for Telnet is 23. So that is Telnet. Now, one problem with Telnet, unfortunately, is that all the traffic, for example, if I was telnetted to R3, which I was just a moment ago, and I typed in configure commands, I typed in show commands, and I got information, everything that went across the wire with Telnet, if an eavesdropper like us was looking at the wire right here, they would be able to see all of our secrets. Anything we typed in, anything the router sent back to us is all in clear text. That's why we don't really encourage anyone in a production environment to use Telnet. The joke is friends don't let friends use Telnet. Now in practice in the lab you can use it all you want, but on a production network you don't want to use it because it's risky, because people can see if they get a hold of those packets and bits, they can see exactly what the content is. So what do we do if we can't use Telnet? Well, instead of Telnet, we can use something much, much better, and that's called Secure Shell. So by launching a Secure Shell, it's exactly the same functionality as Telnet, except Secure Shell encrypts all the data, and as just a side note, it has a different well-known port. It's not the well-known port of 22 that's keeping it secure. It's actually doing a bunch of encryption, but it does have a different well-known port. You can kind of think of HTTPS is to HTTP, what SSH is to Telnet. So SSH is secure for remote connectivity options for management purposes, and Telnet is not. As we go down the list here, we have a couple more that are pretty awesome. One is FTP, and FTP stands for File Transfer Protocol. And how do you launch FTP? Well, it's pretty straightforward. On most computers, you just type FTP, which is a program. It's funny, it's a program, and this is my space symbol right there. But FTP is a program that it happens to be the name of the service. So the same thing is true for Telnet. We typed in Telnet. That was the name of a program which uses the application layer Telnet service. Well, FTP on many computers is a program that uses the FTP service. So you can type FTP space and the IP address of 20.1.2.3 or some other FTP server, and it would send out a session request on port 21. So it'd be to port 21, which is the well-known port for FTP. If you started moving a file with this file transfer protocol, and you started sending a file to or from the FTP server, it would then use port 20 as one of its ports. Now there's a whole bunch of other options available with most of these protocols, but I wanted to focus here on the well-known ports, and I want you to commit them to memory. I think they'll be important. They'll serve you for as long as you work with networking if you're familiar and understand not only the port numbers, but how they operate. One last here in TCP, and I group these together, by the way, based on their layer 4 transport. So all of these are TCP, and the ones down here are UDP. So the last one here is Remote Desktop Protocol. It's used a lot. It's a well-known application, and it has a well-known port. So let's say that at work, you want to be able to go home. So you're hanging off the internet, and you're an end user at your home, and you want to connect and manage your computer at the home office. If policy allows you to do so, you could enable Remote Desktop, the service, running on your PC. And then here at home, you could actually run the Remote Desktop application. Remote Desktop Protocol is what we're using. And it would actually make a request to this computer, again, assuming your computer is reachable through your network, and it would make it to the well-known port of 3389. So these are common, well-known ports for TCP, and now let's take a look at some for UDP. These UDP ones are kind of fun. UDP doesn't care, and that's TCP up here. It cares because it's connection-oriented, meaning you're going to get sequence numberings and acknowledgments, and the TCP header has all of that information built into it. UDP is considered connectionless. It's like throwing a brick over the wall and you hope it makes it. I met this really amazing gentleman, and Ryan. And what Ryan told me, this joke is hilarious. He said, "I've got a joke for you. It's a UDP joke. I hope you get it." And that's the whole joke. It took me a second, like, why is that funny? Oh, it's so funny because with UDP, we don't have any guarantees that it's going to be delivered. We just send it, and we're not expecting acknowledgement or anything else at layer 4 of the OSI reference model. We're just going to send it and hope it makes it. So these applications use UDP as their transport. That's how they're written. So let's take a look at each one of them. First one is NTP. And these aren't the complete list. These are the ones I want you to know and the ones that CompTIA wants you to know. What is NTP? That's Network Time Protocol. And here's how it works. Somebody on the internet's got a really smart computer. And that smart computer knows the exact time of day. So, and they keep it like tied to an atomic clock, and it's just like spot on. So what we can do on your computer here, you can make a request out to that NTP server periodically and say, hey, I'd like to know what time it is because I want to synchronize my clock. You're so smart. You got the good time. I want to synchronize my clock as well. Well, we could use Network Time Protocol to do it, and the destination well-known port for that is port 123, and it's using UDP as the transport. So we send a request, and even though we're not doing acknowledgments for that, we are, however, expecting a response. It's also going to be UDP coming back to us saying, yep, here's the time that I think it is. Enjoy it. Do what you may. So on a Windows machine, do we use that? The answer is yes. In fact, most computers are tied to NTP by default from the factory and have default NTP servers that they check with periodically. And there's a lot of public free NTP servers that you can use as well. So that's NTP. Another really awesome protocol that we're going to talk about right now in a little more detail is called UDP. It's called DHCP. Now, what is that all about? Well, I'd like to show you what that's all about. I'm going to take our computer here and let me bring him in and let's take a look together at the IP address on this PC right now. So my computer right here, the one we've been using all along, if we go to Start and Command Prompt, ipconfig, it says my IP address is 10.1.0.51. But if we do ipconfig/all, as we've done previously, it's also going to show some information such as the DHCP server. Now, what is that exactly? DHCP uses a UDP as its transport and uses a couple well-known ports of 67 and 68. We have mentioned DHCP earlier in our other nuggets, but I'd like to give you a live example of this in action. So I'm going to go to Properties of my network connection, and I'm going to go to show you how it's configured. And there's configured for TCP/IP, and it's configured to obtain an IP address automatically. What this really could say, it could say, I'm using DHCP to get an IP address. And here's how DHCP operates. Let me close that. DHCP allows a computer to make, when it boots up, to make a request saying, hey, I need an IP address. And a DHCP server who's listening on the well-known port for DHCP responds and says, hey, I'm a DHCP server. Here's a beautiful IP address. I think you'll like it. They call it an offer. The client says, great, I like it. I'll take it. And then the server sends an acknowledgement. We have 4 packets to go back and forth, 2 from the client, 2 from the server. And to see it in action, I've got a capture running right now. I'm going to disable the interface on this PC. So it's now disabled. And I'm going to re-enable it, which will trigger the DHCP process to happen again. So I'll click on Enable, and it's coming up. Now, as this process happens, if I don't get an IP address from a DHCP server, meaning I can't find one, or the network's not functioning properly, or somebody forgot to configure a DHCP server, what'll happen is I'll get an automatic private IP address assignment that starts with 169, which basically means good luck. I'm not going to be able to talk to anybody else on this real network. Something went terribly wrong. So we'll go back to our command prompt. We'll clear the screen a little bit, and we'll do an ipconfig. And look at that. We happen to get the same IP address. But you know what? This time, let's take a look at the packet capture that just occurred to verify that DHCP is doing its job. So let's take a look at the DHCP from the Wireshark perspective. Wireshark is a protocol analyzer that's freely available. And again, I'm capturing all the traffic right here off this network link so that I can take a look at all the data that's going back and forth. So the very first, we could call it a packet if we're talking about layer 3. We could say it's a segment if we're dealing with layer 4, or we could call it a frame if we're focusing on layer 2. So this first piece of our DHCP is a DHCP discover. And a good way to remember the 4 elements in a DHCP conversation is DORA, like Dora the Explorer. Doesn't even rhyme. So we have a discover. This first discover is from the client. Take a look at our source MAC address here. Our source MAC address is this number right here, which happens to be the MAC address of my PC, and it's being sent to the destination broadcast address. All Fs and the 12 Fs represent 48 ones. Remember, each F from our IP lesson is 4 bits, 4 on bits. And so we have, basically it's a 48 on destination MAC address. Any device who sees that is going to say, oh my goodness, it might be for me. I'm going to open it up. Now, the switch, if it receives a broadcast like this, is going to forward the frame to all other ports because he doesn't know where the broadcast address lives either. So any device on our network is going to see it. As they de-encapsulate it, they're going to see, oh, this is a UDP. It's for destination port 67, and only DHCP servers are listening on that well-known port of 67. Everybody else would drop it, and a DHCP server hopefully would respond. Our source port for DHCP is 68. So 68 is a well-known port that the client uses, and 67 is the well-known port the server listens on. If we take this down, the next packet, we have a response from the server, and now this response is going back to the client at the well-known port of 68, from the server source 67. It's offering the IP address, and then we have the request, which is the client saying, you know what, I'll take it. It's great. I love that IP address. And then finally, we have an acknowledgement. And in that acknowledgement, we could hand out details such as, if we scroll down a little bit, such as what the IP address is, of course. Obviously, that's there as a confirmation. But we also have things like the default gateway, who the DHCP server was. Scroll down a little more. Right here. Who the DNS server is, who the default gateway is, and these are all called options that we are given as part of the DHCP conversation. So again, the acronym, if you want an acronym to remember these steps, you could say it is DORA, as in Dora the Explorer. Discover, which is the client looking for an IP address, and offer, which is the server saying, yeah, I've got an IP address. If you want it, you can have it from this pool of addresses. Client saying, I'll take it, and then the server doing a final acknowledgement back saying, you know what, I understand you're going to take that address. Here's some additional information. Have a good time with it, such as things like the DNS server and the default gateway, which are right there. All right, so that's this part of our journey, and there's two other little pieces, and then this nugget is going to be complete. Check this out. I think you're going to like this. If we're dealing, let me move this out of the way. If we're dealing with a server out on the internet, like Google, like in our first example, where the client went to Google, how in the world did this client know that the IP address of Google was whatever it happened to be, 77 or whatever the IP address is? The answer is it uses a service called DNS. On the internet, DNS stands for Domain Name System. And DNS servers collectively, they know about all the IP addresses. What do you mean, Keith? IP addresses. They know if you give them a name, say, hey, what's the IP address of google.com? They will give you an answer. They know. We'll have a separate lesson just on DNS and how it works. But for this purpose, the client is also configured with its DNS server. And it learned that through DHCP. So if I need to know what the IP address is of google.com, I make a request out to the DNS server who's listening on port 53, and then the server gives me a reply back saying what the IP address is. Once I know what the IP address of Google is, I can then say, is the IP address of Google, is it local here on my network, which is 10.1.0 in this case, and let's say Google's at 70 something, and the client says, no, that's not local, and it will format a packet to be sent to the IP address of google.com, but at layer 2, it'll use the layer 2 address of its default gateway, so this default gateway can look at that IP address and make a forwarding decision, hopefully in the direction of google.com. The last one I put up here is TFTP, and TFTP stands for the Trivial File Transfer Protocol. So up here we have FTP, which uses TCP, and TCP is reliable. It uses connections, and it sets up logical sessions, and it sets up acknowledgments and uses sequence numbers. It's like registered mail. Well, Trivial File Transfer Protocol is another application layer service, but this one uses UDP, and it doesn't do any tracking. So that means that it's going to use UDP. It's going to be less overhead, but it's not as reliable. And the well-known port for a TFTP server, a Trivial File Transport Protocol server, is 69. So in this nugget, we've taken a look at the well-known ports for a bunch of very, very common application layer services that use TCP and some that use UDP. Now, why is this important to know? Well, there's a couple reasons. Number one, CompTIA certification for Network Plus is expecting you to know these. But for the real world, understanding what these protocol numbers are will assist you as you troubleshoot networks and work with things like access control lists, where you might have certain ports and or protocols that are being stopped along the way. I have really had a lot of fun discussing the well-known ports with you. I hope this has been informative for you, and I'd like to thank you for viewing.